Hello and welcome, guys. Today we are talking about Star Trek, relativity, and FTL, faster than light, communications, travel, what confusion it adds to physics. So let's get started. So, FTL and subspace communication. Let's look at what subspace communication is in Star Trek world. Subspace communication or subspace radio, hyperchannel. It's the primary form of electromagnetic communication used throughout the Federation, and the transmission of subspace radio signal which traveled through subspace rather than the normal space, this was permitted at faster than the speed of light. This made it much more practical than conventional radio. In fact, starships that were so far out in space could receive communication almost instantly rather than with a lot of lag. So that makes this whole Star Trek design so seamless as we travel over vast distances in space. Now, the problem comes when we start looking at relativity physics and what it means to time in context of this FTL that Star Trek shows. There is two significant things that you need to observe when you apply relativity to Star Trek. One is that the time itself depends on the reference frame in which we are observing, because the max speed is bounded by velocity of light, which is c, and then the frame in which we are, let's say it's moving at velocity v, the time perceived in that reference frame is not going to be the same as the time originally perceived. The second thing of consequence here is this concept that Minkowski shows that, given any point in space, what is causality? What does causality mean to us applying relativity physics? Is that from any given point in time, you can draw a light cone into the future. Here, time is the vertical axis, and space is really the horizontal axis. And so when you draw this kind of diagram, this is obviously only done here for two-dimensional space, and the third dimension is time, but it should be possible in some other more complex diagram to show this in higher dimensions. But the important thing to understand is that in this case, because velocity of light um, is the maximum velocity with which any signal, anything, any information can travel in our known world, which is the laws of physics. So what happens is that it makes a cone. And what is the significance of this cone? Well, causality is bounded by this cone. So if an event happens here at any point, let's say at this vertex of this cone, it can only affect objects that lie within this cone because light itself cannot travel faster than this. So it cannot reach a point outside, it cannot reach a point in space that's outside this. Therefore, an event which is happening here cannot be the cause of another event that is outside this. So that is our conventional understanding of causality, which is A implies B because A was the cause of B. If you do something, let's say if you shoot a bullet from a gun and it hits an object, then the shooting of that bullet was the cause and the hitting of the object was the result of that. And it cannot be backwards in our conventional sense of thinking that the object is not hit first and then you shoot the bullet. That's not, we are not used to that way of thinking. And so causality to us means that when something happens, first the cause happens and then its effect happens. That's our conventional way of thinking. And so what Einstein showed us was that as long as the velocity of light and everything falls within the velocity of light, nothing travels faster than this light cone, then everything is bounded. And no matter what reference frame you choose, as long as every reference frame is bounded also by the speed of light, then the causality, which is if an event precedes the effect, um, or the event is the cause and something else is the effect, it all lies within this light cone. Now, as soon as you say, oh no, the FTL is possible, subspace communication is possible, that means an event here is also connected to an event here, here, and anywhere in the space here. So that is the problem. Now let's see in terms of relativity physics, what does that really mean? What will break if we do that? In fact, Einstein himself thought about this experiment that we're going to cover next. And that experiment, also known as the Toleman's paradox, is that if we go through this faster than light communication, something will break in relativity physics, and that is what we're going to talk about. Einstein and Arnold Sommerfeld in 1910 described this as a means to telegraph, or telegraph is an older term. It's like make a call into the past. A device capable of telegraphing into the past was later also called as tachyonic anti-telephone by Gregory Benford. Now, you can you can search for this term tachyonic anti-telephone, and there's lots of literature available on this. But in a sense, we'll describe this idea in great simplicity, so that we can understand this. So let's look at the basic idea, which is, let's say that you have a point in space which is A, and let's say some origin is here, which is distance 0, and this point is A distance away, and this another point is B distance away. And if we send a signal which is at FTL, right, which is the cause would be here, let's say you shoot a bullet and it's received here, and this bullet is traveling at faster than speed of light, which is speed is a, and it's received and it hits an object here, right? So there are two events that happen: the sending of this bullet and the receiving and hitting the target, and large distances away, and then this traversal is at speed a, which is larger than speed of light. So in this still reference frame, this reference frame, let's say, is not moving. So what would you see this time difference to be? This time difference is just going to be b minus a over a, where a is the speed of the signal or the event, whatever this is. Let's say it's a bullet or some signal being transmitted. It's being transmitted, it's being received. And so this is a simple equation, even from Newton's laws of motion. Very simple. Now, when you next look at another object that, or a reference frame that is moving, that's not still, but it's moving with a velocity v, these two exact same events, how do they appear in the reference frame of another object? Let's say a ship, and it's not really moving very fast. Let's say the ship is moving below the speed of light. Let's say this v is half the speed of light, which is, yeah, fairly possible to do. So let's say, and I guess it's not really possible to do in today's world, in today's physics, because it takes huge amounts of energy to even approach the speed of light. So um, take my words with a grain of salt, but let's say that we could approach this velocity of light to, let's say, some factor, let's say c by 2, and let's say this is the reference frame in which we are moving in the ship at half the speed of light. And now let's observe these two same events, that is the signal being sent from A to B, and let's see what happens. So when you apply Lorentz transformation, that's the way in which relativity would look at when a moving reference frame is involved, and I look at, let's say delta x is the distance between A and B, which is nothing but B minus A, and then delta t is the time in the still reference frame, which was the original reference frame in which was not moving. So delta t was really B minus A over A, which we saw earlier. Now, in this new reference frame, which is this moving ship that is moving at velocity v, now what will happen? So this Lorentz transform will describe, in terms of relative physics, that what is the delta time seen by this second, let's say this ship that's moving at half the speed of light, what would it see? So it would see this, where this gamma is this factor, or the Lorentz factor. Um, Now, this is the equation. Now, let's simplify this, because we know delta x is really, from the original reference frame, we can write this as delta t times a, which is nothing but the speed of the signal, right? So because we know that from the first equation. If we substitute this, then really what happens is, let's just take a pencil out. And then this will translate into that. Now, why is this so critical? Because this equation is what Einstein thought about, because even at our proposed speeds, like the velocity of the ship was c over 2, so this is still a positive factor because this is square root of zero point 0.5, and so this is okay. But imagine what happens to this factor, right? Because if, let's say, a, which is the FTL communication, was 5 times c, and this v is c over 2. So let's see what happens here. So if we multiply these two terms, what you are really getting is 2.5 c squared. So 2.5 c squared, c squared cancels out, so 1 minus 2.5. This term goes to negative 1.5. And so what is happening is that the delta t here in this new reference frame and the delta t here are related by a negative sign, right? This delta t prime is negative 1.5 times delta t. So if in the original reference frame it took some time, in this time is negative, and the event B will seem to happen first, and the event A would happen later. In effect, the cause happens after the effect, right? So that is the dilemma that Einstein thought about. And Paul Ehrenfest, he's another physicist, he drew a Minkowski diagram to show how this problem manifests in terms of visually, and you can see that on the Wikipedia page. But that is the problem, right? So we can see that the time, and time for us in our world, is really causality. And so when we look at this, we can see that this is not something that we are used to seeing, and this is the problem. And Einstein and similarly Tolman concluded that this result contains, in their view, no logical contradiction. He said, however, that it contradicts the totality of our experience. So that's the impossibility. If A is greater than C, which is FTL communication, seems that that's impossible, and that's sufficiently proven from our experience, right? And so that's kind of the key idea, that Einstein and Tolman thought that FTL is not possible, because if FTL appears to happen, then the causality as we know it might break, and different reference frames will see this signal transmission in a weird fashion where causality would be broken. So I would probably leave this kind of hanging, because I've not really shown the effects of FTL, and especially episodes in Star Trek, where tomorrow is yesterday, where we're talking about a whole ship going backwards in time using slingshot effects, things like that, where we really talk about how we are going to travel in time. All we tackled in this video is really the subspace communication. Even if we could communicate at faster than speed of light, let's say some tachyonic telephone was available that could make a call into faster than speed of light signals, that still would cause so much problems. It would cause the breaking of the relativity of simultaneity, which is a foundation of our experience today, right? So maybe whole new physics would have to evolve to explain all this, but relativity does not really like FTL, and this thought experiment, is something that solidifies this understanding. So hopefully you guys enjoyed this video. If you did, give me a thumbs up and subscribe to my channel if you have not, for more such content into the future. And until then, take care and bye-bye.